Hello, am I audible?
So we will begin with the next talk session. The next talk session is chaired by Professor M.P. Rajan. And there is one more talk session going on parallelly in the lecture hall 1 complex. And we will begin with this one.
Good evening, all of you. Next talk is by Professor Anirban. He doesn't need a special introduction because he is here for the last 3 days. Yet it is my duty to introduce him. Dr. Anirban is a professor in Punjab University, in the School of Engineering and Technology. Basically, he is a physics. Got PhD from Saha Institute of Nuclear Physics, Kolkata. His research interests are econophysics and the data science. We know that in the modern era, the financial market plays a key role in the economic development of any nation. The financial market is so complex in the sense that the dynamics of the financial market is very uncertain and unpredictable. So today we will hear from Professor Anirban on deciphering complexity of financial market.
Thank you very much, Professor Rajan, for the kind introduction. And this talk will be very different from the other mathematics talks that were going on probably. And so I'll go very slowly initially to explain the philosophy behind the works that I will be presenting. But then I'll be accelerating when we come to more maths. I think all of you are familiar with the concepts. So I wanted to acknowledge all my collaborators actually with whom I've been working for several years. This is Dr. Kiran Sharma, she's a computer scientist. First, Shishir and Rajiv were actually Pfizer Pune gaming students. Now they're doing PhD with me. Dr. Shori Shas is from CNI, Dr. Shubha Bhatter from Australia, both of them are statisticians. Anindo is an economist in Ahmedabad. Rakesh, Hitesh, also a Thomas physicist. And Arijit Samal is a mathematical biologist. I have a very interdisciplinary team. And I will be explaining much of the work we have done. I wanted to give a small introduction about myself. So I was almost like a random walker on the surface of the earth. So I was born and brought up in Lajin, very beautiful place. I think all of you know because of its tea, and also for the very nice mountain ranges at the back. It's Mount Kanchenjunga. I went to St. Joseph's in Mount Auburn for my schooling. And after spending 18 years of my life in Darjeeling, I went to Scottish Church College in Kolkata for my bachelor's, and then University of Calcutta Science College at Raja Bazar. I completed my PhD from Shah Institute of Nuclear Physics, as Professor Rajan mentioned, and later I also completed what is called the habilitation or exam, I think, equivalent of a DSc from University Pierre and Marie Curie, which is Paris. For my postdoc, I spent a little time in Helsinki University of Technology for 14 months. And then I went to Brookhaven National Lab, which is very famous for particle accelerator. So you see the relativistic area and collider at the background. Then I came back to Venice Hindu University as a lecturer in theoretical physics. I spent 3 years. And then I was offered a permanent position at a very prestigious engineering school. It's called École Centrale Paris. So Eiffel Tower, Gustave Eiffel. All the French car makers that you know of, Renault, Peugeot, Citroën, tire maker Michelin, they are all ex-students of this university. So they're famous for automobile, hydrodynamics, and other. Then I was offered a permanent position at the School of Computation and Integrative Sciences in Jawaharlal Nehru. So I returned to India in 2014. And only from June this year, I've been as the Dean of Research in the School of Engineering Technology for BM and Punjab, which I've already introduced on the first day of the conference. I've been mostly working in complexity science, and I wanted to introduce what the idea behind is. So already seen that we've been hit by the pandemic for more than 1.5 years. And when the pandemic thing had just begun, this was in April 2020, when there was an article in BBC that it will lead to one of the worst economic crises since the 1930s depression in the Americas. Now, we've seen the world evolving and a lot of things happening. There was one very nice article I wanted to point out. This is the damage we are not attending to. This was written by two former directors of the Santa Fe Institute of Complexity Science. And those who attended the talk yesterday of Professor Ravi Karandikar, they begin this article with the same, of this airplanes being hit and data being collected. And what they actually prescribe is that we need an integral approach, a complexity science approach, and I'll explain to you what that is. So you would have seen that our Bombay Stock Exchange Index, the prices go up and down, and often it's connected to the socio-economic events of the country, even political sometimes. And when the corona thing was hit, it actually crashed. And then again, when the vaccine was approved, it went up. Okay, so often the events in the globe dictate the movements in the prices of the stock exchange. And even though we have been going, people were really not understanding why the Sensex was on fire. So this is a wonderful blog article written by Anirban Chakraborti in NDTV. You'll find this. It's counterintuitive. When we are saying that we are hit by economic crisis, why is the stock market doing so well? Right? Why is it on fire? So I would ask you to actually read it. Very simple article. Now, statisticians and mathematicians have been trying to predict the prices for very long. This was actually first time in American Statistical Association bulletin, and it's like 1910 when they were trying to predict the prices of corn and using regression techniques. Later, in 1913, there was another article which was published in the American Economic Review. Again, methods of business forecasting based on fundamental statistics. So as yesterday we were seeing that people have often analyzed data in order to predict what can happen in the next few months or years, and how things would move. Now, global financial markets, like Professor Karandikar explained, we often have tick by tick data. That means every millisecond data is pouring in. Every click that you do, every bank transaction that you do, every financial transaction that you do is recorded in the form of digital records. So there's a huge amount of data, and that's why there's a lot of scope in the financial world. Now, what is interesting is that, and I wanted to draw your attention to this part, this is economic data. This is borrowed from a slide of Joan Farmer, who was also in the Santa Fe Institute previously. He's a physicist at nonlinear dynamics, the person. Now he's heading the new economic thinking in Oxford University. He pointed out that if you see the price changes, all the basic amenities, hospital services, college tuitions, education, childcare, they have been steadily rising. Whereas, all the luxury items which we used to think, television, toy, computers, telephones, they have been steadily decreasing. Now, when I am a government, I want to frame my public policy. Now, these are the things that we must often take into account, right? And we are not normally bothered, as long as the prices of these things go down, we think, world is doing well, we are doing well. But you see that, the basic amenities have been rising steadily, and that's not good for the society. So often the public policy have to be done based on, data science. Now, data science is going to be a very important paradigm. So, this is again borrowed from another colleague of mine, So she showed this cartoon where it says that in the first many centuries we had empirical observations, then we had theoretical modeling, then the computational sciences, and today we are in the data science technique. Now, what is interesting is a quote by Nobel laureate from economics, Herbert Simon, is that perhaps the right way to move is to understand before one predicts. So often we are, interested in prediction, but first we have to understand. Then we can predict. That's what I have been doing. So I wanted to tell you about the philosophy. Also because this is another cartoon that says Remember, the other team is counting on big data insights based on previous things. So keep the ball with your other foot. Now, this is a problem because we are all parts of this complex adaptive system. So people often adapt. And that I tell when I'm doing financial math. Because suppose I predict that there will be a crash next Friday. What will happen is people will often panic, react, and then it will happen tomorrow. So I can't prevent the crash. Right? We're all part of the system. Now, the same tools and techniques that I'll be presenting can be also applied to different other systems, like time series analysis, wherever you think. So, predicting earthquakes or cyclones or weather forecasts. We ourselves have been doing a lot of modeling in environmental and climate change, which I won't cover here, or in biology. So, I'm going to show a very general set of tools and techniques, and so what I thought is very important is bridging the data and science. And this is what I think Professor Karandikar was also mentioning. You have to have domain knowledge, and then you do the data science, and you have to work as a team. So that's what's very important, bridging the data and science. Right? Now, traditionally, how science has been done is what we call the picture of reductionism. Right? So suppose I ask, what am I made up of? So you say that I'm made up of biological tissues and cells. Right? What are the cells made up of? Different organelles like chromosome, ribosome, microsome. What is the chromosome made up of? It's made of the DNA. What is the DNA made up of? Chemical elements. What are the elements? Like atoms. What are the atoms? Electrons, neutrons, protons. What are the neutrons and protons? They're made up of quarks and non-bicupluons. So that's the reductionist picture. So we start to bake influences. Now it has a lot of limitations. So there was a wonderful article written by the late Phil W. Anderson, who is another Nobel laureate in physics. He said that more is different. So the way I described it, you might think that going from biology to chemistry to physics and particle physics, there's a hierarchy in the sciences. And truly speaking, you can roughly linearly arrange them that way. However, one science is completely different from the science that precedes in that hierarchy. Because at each level, you have entirely new laws, concepts, and generalizations. And so if I tell you everything about the properties of the quarks and gluons and electrons and protons, I won't be able to explain how the universe works or how our society works. Right? So often what you need is a bottom-up approach, and that's called integrative approach of complexity science. Okay? So instead of looking, in silo, we have to have a holistic approach. That's often what we follow in complexity science. Okay? So that's the rationale behind much of my studies. And it was very encouraging that this year the Nobel Prize in Physics went to actually complex systems, where Giorgio Panisi, I have attended that in his courses when I just started my PhD. He is on spin glass theory. And so we wrote an article, also one of my colleagues and myself, that why the Nobel Prize in Physics for complex systems will change the way we look at science in India. Okay. So we need to have a different way of looking at it. So what do we mean by complex systems? Typically, these are made up of different smaller parts or constituents, but the whole is not exactly the sum of its parts. And often you have nonlinearity, emergence, continuous ordering, adaptation, feedback loops. So if you go to Wikipedia, you'll see something like this. And in my own research, I have used all these different things: networks, selective behavior, game theory, nonlinear dynamics, pattern formation, to attack these problems. So in 2008, as yesterday also Professor Karandikar was saying, that we had a big financial crisis, which was called the subprime crisis. And three of the largest banks, Lehman Brothers, Merrill Lynch, AIG, and all, crashed. And there were a series of articles criticizing the approaches of economics. And this was written by Thomas Crookes and Frank Westerhoff, who were both economics, very famous economists actually. And they said that economics theory offers policymakers little guidance about what to do in the current situation. And so economics should take stock of the experience of the natural sciences in handling complex systems with strong interactions. That's where physicists are very used to handling things. Similarly, there were two other articles that economics needs agent-based modeling, complexity theory, and financial. So these are some of the things which have motivated me in the last many years to do research in this field. So most of these things that we do is also called economic physics, where we try to apply the tools of physics to solving problems in economics and finance, or to solve problems in sociology, which we call sociology. And in the past many years, I've edited several books with different types of focus areas. And I have two books also on from Cambridge on economic physics of income and wealth distributions. And the other one is many other books, which is stock market model. I won't have time to go into all those details. And if you are interested in some of these articles, you'll find some review articles here. And this one has 30 articles written by 40 different scientists from different countries. And you can find if you want to find some. So one picture that normally we often use is called a network picture. And you might be familiar with networks. The internet is a big example of a network. Social media, friendship network, as you've seen in Facebook, or your own collaboration networks. Every time I write a paper with some of my co-authors, I make a research collaboration network. So there can be different types of networks. Now, what we have been doing is applying this network theory, for example, to study how languages diffuse in space and time. Okay. Or we've been also working on ethnic conflicts, human rights violations, terrorist attacks. So whenever you give me spatio-temporal data, that this is a terrorist event because occurred in such and such latitude, longitude, using certain techniques, I can convert them into networks. And then once I have the network, I can study the characteristics of the network, topological properties of the network. And often that becomes very important. Suppose I want to have a counter in terrorism unit. Yeah. How would I concentrate? I have always limited resources. I don't have so much police personnel or intelligence personnel to monitor the entire country. How would I allocate? Or like what we were telling yesterday, vaccination. So every time we come in contact, the disease spreads. Now, whom do we vaccinate? Should we? So India took a policy that initially they said that everybody who was 60 years and over would get the thing. Then 45 years and comorbidity. Then they said, okay, everybody above 45 years. It worked well. Then they said everybody above 18, and then the whole policy failed actually. There were not enough vaccines. Now, you have to see the effect of the vaccine also. The elderly people were being affected initially, but there were also people, young people who were going to work. Who should I vaccinate them first, or should I vaccinate them? Now, we are all connected in networks. So often these pictures become very important. Okay, so that's what we've been studying. To come back to our topic, I can also create financial networks. These are slightly different from the others because these are inferential networks. You don't really have, physical connection between two stock prices. How do I construct the network? So I have a series of papers, and I've been looking at different levels of the stock market. One is microscopic level of the stock prices, then sector level, which we call mesoscopic, and then macroscopic level, where we have different market indices across the globe. Okay, and we had a series of papers starting from random matrix theory, which is applied in physics and biology and many other places, to geometry, network geometry, and also topological things. So I'll give you a flavor of what type of techniques we use. I won't be able to go to the details because we have very limited time. So as I told you, financial market is a very interesting system because it is an ideal system and a complex thing, right? And I don't know if you know that Louis Vechelier, who got his PhD under Henri Poincaré in 1900, he had worked first time on the modeling of bond prices in the Paris bourse. And he actually derived the random walk theory 5 years before Albert Einstein. If you see the derivation, and you have his French paper in École Normale Supérieure Library, you'll see that's the derivation which we mostly follow even in physics textbooks. So Albert Einstein's approach to random walk theory was a very different one. And during his lifetime, he did not get the recognition, Louis Vechelier. He was one of the first one to formulate random walk theory. Now, physicists and mathematicians have already started chaotic theory, Gauch models, which are like multiplicative stochastic processes. But this SP500, which I showed here, is much more complex time series. And like as Mr. Rajan mentioned, these are very complex dynamical systems. And that's where attracted physicists. Now, what we do, as I was saying, is we look at two stock prices. So these are the adjusted post prices of two companies. I construct the logarithmic returns. When I do the logarithm, it becomes a stationary process in a short window. Okay? And then I compute the correlation coefficients between each of these return times. Okay, so I and J are two companies. I will take the returns of this and look at the correlation. I can also see how they evolve. So this is 194 stock prices over 32 years in the New York Stock Exchange. Okay. 194 because those are the ones which started in 85 get released. Okay. Otherwise, I could have a larger correlation. Now, what is interesting is that sometimes the market is extremely correlated. This shows you the parameter. So +1 is extremely correlated, -1 is anti-correlated. So sometimes you find the market is extremely correlated. Other times it is much less. You will see clear blocks which are. So what is interesting is that if I look at the correlation coefficients and look at the distribution, you find that sometimes they are heavily skewed and have a different distribution. When I plot the mean correlation, you find that this is the thing. And exactly when the mean correlation is very high, these are the places where we have market crashes. So you can actually look at when there are these big market crashes happening, how volatile it is. So you can look at the mean correlation or the volatility, which is the variance, or you can look at the risk, minimum risk, which we calculate using Markowitz portfolio. Now, why are these things very important? These crashes, because those are the times that the market is very volatile and there is huge amount of what we call homogeneity. Now, there was a very interesting article, this is called Anticipating Critical Transitions in Science by the group of Schaffer. And they showed that, not only in financial market, many of the complex systems that I was studying, we have the same observation that during normal time, you have modularity and heterogeneity. And during crisis, you will have connectivity, high connectivity, and homogeneity. Now, this is exactly what we showed using, again, financial stock market prices and these correlation networks. So if you want to go in details, you can refer to this paper. Now, as I was saying that I can compute this correlation coefficient between any two stocks. I can also make a transformation and create a distance net. The advantage of this definition is it also makes a larger metric, which is useful for keeping the topology intact. So what we did is we had several papers where we used this type of what we call minimum spanning tree or multi-dimensional scaling, starting from this distances. So if I am given the distances, suppose between 4 cities, Delhi, Kolkata, Delhi, Chennai, Delhi, Mumbai, and maybe Delhi, Chennai. And then can I construct a map from this distance metric? So that's what multi-dimensional scaling does. On the other hand, if I have these distances, can I connect it all the nodes using the minimum, sum of the distances minimum? That's the minimum spanning tree. So I'm sure most of you are familiar with it. So then I can get a map or a network picture from the stock market prices. So on the left, I show something in New York Stock Exchange. This one is from the CAC 40, or in French is called CAC 40. You'll see that this is during the Lehman Brothers crash, when Lehman Brothers was behaving very differently from the rest of the companies. Now what we can do is once I have this correlation frame, so these are computed over short windows of 40 days, and I see how it evolves. I can look also at the L1 norm distance, the similarity between each of these matrices, between 1 and 2, 1 and 3, 1 and 4. And then if I plot, I'll see that, okay, there is this distance is shown here with different color code. And market is very different in these. These are either the crashes or the bubbles. Now it is very difficult to detect when you are in a bubble. So a few years ago, we were in a real estate bubble. In fact, in Delhi, you still have a real estate bubble going on. And soon it will crash. So when it crashes, then you have a problem. Okay. So it's important to detect when you are having a bubble, when you are approaching a crash. So what you do is, for example, I have these similarity points. I have 800 such points, 800 such correlation matrices. We make a three-dimensional, multi-dimensional scaling map. Now, any of these magenta colors are actually similar to this. Any of these blue ones are similar to this. Any of the green ones are similar to this. And all the black ones are similar. So you see, using a clustering algorithm, I have actually shown that there are 4 dominant groups. And most of these patterns belong to these 4 groups. Now, once I know this, I can actually go back in history and find out which frame belong to which group, S1, S2, S3, S4. So these are like some of the states of the market. And then what you can do is you can actually look at the transition probability. How many times we jump from 1 to 2, 1 to 3, 1 to 4, and you can construct it. And then you will find it's almost impossible that when its market is an S1, it will jump to S4 when we have a crash. So all these ones which are in S4 are this which will indicate market crashes. Okay. So this type of tool helps you to monitor the state of the financial system. So if I want to do a continuous monitoring, so like I do my blood pressure check or a thermal scanner check, I can do what is the state of the financial system. Next, I'll just give you an idea how much time do I have. Okay. Right. So what we can do is also, you remember your PVT diagram in water, different phases. Right? So what we did is, starting from the correlation matrices, for each of these matrices, we calculate what is called the eigenvector centrality. Right? And then from this eigenvector centrality, we constructed a entropy. And what we did was like this. Any correlation matrix can be decomposed into partial correlation matrices. And in finance, it's conventional to have a market mode, a group mode, and the random mode. Market mode is very far away, which represents the average correlation. The group modes are these deviations, and the bulk of them follow the random matrix, which is the market mass distribution. So each of these matrices can be then decomposed into these CM, CD, CR. And from each of them, I can compute an entropy function. And then if you carefully choose the variables, these are this H, HM, and HM, and I'm showing how it varies across time. So this is the market index of USA. This is the mean market correlation as I was showing. These are all these crashes that are happening. And this is how the H, HM, and HK are doing. Now, if I combine these variables in a certain way, you will find that there is a phase separation. So all the market crashes appear here, all the bubbles and bubble bursts appear there, all the anomalies. In fact, what happens is like this. We did study for 2 different markets, and we showed that if I plot the absolute value of H minus HM and H minus HM, you will find all the normal periods when the market is like the normal. These are the gray spots. All the crashes happen here, all the bubbles here, bubble bursts, and there is sort of a data collapse. So if I plot H minus HM versus the mean, which is the mean market correlation, all of the data collapses. And that happens not only for US market, also for Japan. We went further and showed that suppose I look at the Black Monday crash. What happened? It was here, that was 19th October 1987. It went to this red part, then came. If I have a bubble, then it goes like this, goes to the burst, and then it comes back. So it's like in physics what we call order disorder transition. Okay, so you have an order disorder transition. Whenever I have a market crash or a bubble, I have these steps. And we found that this is true for many other markets. So I'm not going into the details. What we can also do is once I build a network, I can use all the geometric ideas. So like discrete curvature, leaky curvature that we were seeing yesterday, we can compute for the Forman leaky curvature for a network. And then look at how the Forman leaky curvature varies over this time. So we had this paper, Network Geometry and Market Instability, and we found that it can pick up all those bubbles and crashes extremely well. So these are all the periods when I'm looking at the Forman leaky curvature and seeing the risk. Okay. Similarly, what we can do is monitor very closely and see what happens, the modularity and the heterogeneity, like I was saying. So during a bubble, it will behave one way, during a crash, it will behave in another way. Similarly, we did the study for all the global market indices. I will not go into details. We can also use topological data analysis. I'm very sure that you're familiar with the topological concepts. So sometimes, we tease the mathematicians that they don't know the difference between a donut and a cup. There's this continuous transformation which will change the now, or the cow and a sphere. There's topologically no difference. Right? Now, what we can do is we can construct simplicial this and look at how the homology changes. So persistent homology. I'm sure you are familiar. If not, I will tell you this later. So you have this parameter epsilon from which you can construct this simplicity. And failing that, you look at persistent homology. So all this H0, H1, H2, which are the Betti numbers, you can see how it evolves over time. So we've done similar things for the, you have a metric data set, and then you can have this persistence diagram. So for a circle without any noise, it will look like this. A circle with noise, it will look like this. So when we have these matrices, I can draw these networks, and then I can draw this persistent diagram. Once I have these persistent diagrams, I can again capture the bubbles and the crashes. Okay, so I just gave you the flavor of the different type of tools and techniques that we've been using in data science. And I wanted to bring that to think that we need to understand the data and the science behind it. Okay. These are some of my papers, and thank you for your attention.
Any questions from audience? Any questions from the online?
Yes.
The very first part of your presentation, you mentioned about some networks that was built based on some inferences. Since it is a big, those networks are built based on inferences. Those networks also have some uncertainty. Morphology is uncertain.
Uncertain. That's why. Yeah. So that is why this topological data analysis can be very useful. So if there is noise, you can understand that which are the structures present there, not because of the noise. Eliminate the noise and then pick up the structure. Similarly, the ones which I showed you using the minimum spanning tree and the random matrix theory, you can eliminate the noise using the random matrix theory, find out the relevant information, and then build the network.
My question is,
yeah.
Is there any mathematical evidence to quantify the morphology of the network? Determine how one network is different from another.
Right. So there are different characteristics. So some look at the distribution, some look at there are different topologies. So they compare between different types of networks. Yeah. And this topological data analysis can also be used to quantify those.
Any other questions? So I have a question.
Yeah.
So you have taken the correlation between the stocks.
Right.
So what about the serial correlation?
What about
Serial correlation?
mean
Each stock itself has serially
oh,
correlated.
the autocorrelation?
Yes.
Yeah. So the autocorrelation in these daily, so here I have used the daily stock prices.
Yeah.
So normally what happens is beyond a few minutes, the autocorrelation dies, stock prices. Now for daily prices, you often find it, but again, you can look at, suppose we, depending on the windows we are taking and how we are evolving, you'll see sometimes, most of the time you will not have the autocorrelations. Okay.
Second thing is that so you are trying to transform this as a map. Then you apply the clustering algorithm.
Yeah.
So what is the motivation for that one? Instead of that, why don't you go for a clustering algorithm with the distance measures?
Yeah. So that's what we have done. One is that I look at the once I have the distance, I can create a minimum spanning tree or sort of a network, and then look at it's a hierarchical clustering method, so you will get the clustering. But often what happens is that you will be, when you are doing a hierarchical clustering, you will be using some cutoffs or filtering, right? So most of these minimum spanning tree, all those type of things, or other threshold networks will have some, bias. Okay. The good thing about multi-dimensional scaling is you don't make any assumptions. You take the data convert it into distance, and then see, so all the similar objects will be placed together, all the dissimilar will be placed far apart, and you don't lose any information. So that's the advantage of the map, and then I do the cluster.
Okay, so let us give a big hands to him. Thank you.